Hello, everyone. Welcome back. Thank you for joining us. I'm Steve.
And I'm Scott.
And together we're Backyard Musings. We are in the backyard, Apple Valley.
And we are talking science and technology.
Yes, this is an interesting one. We've been talking about quantum computing, but this is quantum battery.
Well, we've been talking about better batteries than lithium, right? We've talked about several different kinds.
But never a quantum battery. This is a little bit over my head on this one. In the world of next-gen energy.
I'm sorry to hear that.
Yeah. In the world of next-gen energy, researchers are taking a leap beyond chemistry into the strange rules of quantum mechanics. A new type of battery known as a quantum battery is no longer just a theoretical dream. Thanks to a team from RMIT University and Australia's National Science Agency, CSIRO, the path toward efficient ultrafast energy storage just got clearer. Would you like to know more?
So what does that R stand for? Do you think it stands for the
Royal. Because it's Australia.
Royal.
Something Institute Technology, not Massachusetts. So.
Yeah. Okay, here we go. Quantum batteries don't rely on chemical reactions like the lithium-ion versions powering your phone or car. Instead, they store and transfer energy using quantum systems, tiny building blocks like atoms, molecules, and light.
Okay.
At their core, they use quantum effects like superposition and entanglement to potentially charge faster and perform better. Researchers believe these batteries could someday improve solar panels and power microelectronics.
Like that pacemaker, the little thin one, like that could power that.
Okay.
But we talked about that like a couple months ago. Mm-hmm. But there's been a big problem. While they charge quickly, quantum batteries have struggled to keep that energy for long. Earlier versions lost energy in a flash within nanoseconds, making them impractical. Now, a new approach developed by scientists at RMIT and CSIRO has extended energy storage time by over 1,000 times, marking a major step toward real-world use.
That's pretty substantial.
Yeah.
Traditional batteries have changed how we live, especially with their role in electric vehicles, smart devices, and the growing need to store solar and wind power. Still, they aren't perfect. Lithium-ion batteries, the most common kind, degrade quickly and need frequent replacement. They're also slow to charge and aren't well suited for advanced applications where speed and efficiency matters most. Now, I will have to say a plug here, and these people are not a sponsor, but I run Milwaukee power tools.
Yeah.
And the battery operated ones, M12s, M18s. And those batteries are amazing.
Mm-hmm.
I can use an M12 battery, which is a small battery. Again, not a plug, but I can use that battery, and it's lithium. I can use that battery all day long, multiple days without recharging. So they've got some kind of a good deal going. Now, I don't know how other companies are because I don't have those.
Maybe it's proprietary,
like the yellow and black brand or whatever. I don't have that. So,
no,
but anyway, they're good batteries.
The brand that shall not be named.
DeWalt. I don't have DeWalt. I got DeWalt power tools, but I don't have DeWalt battery power tools. So, anyway.
All right, quantum batteries aim to solve these problems. The idea is to use excited states in atoms or molecules to store energy. Energy is then released by shifting those states through quantum transitions. Because of the collective behavior of quantum systems, adding more particles doesn't just increase energy linearly, it can actually speed up charging through what's known as a square root n-fold boost. This quantum speed up means the more units you add, the faster the system charges. I'm trying to wrap my head around this, and I can't, man. Okay, let's get the slide up. Here we go. Okay, we got a slide for you.
The Dickey quantum battery is a model that embodies this idea. Named after physicist Robert Dickey, we hope we're pronouncing his name right. It involves a group of emitters interacting with light in a special structure called an optical cavity. When done right, this setup allows for super absorption, a rapid intake of energy. The more emitters inside the cavity, the faster the system charges. Scientists confirm this in experiments using organic optical microcavities where charging rates increase significantly with molecule number.
See, this again, organic microcavities. I mean, organic is living tissue. I'm not wrapping my head around this. Like maybe your eye socket? I don't know. Super absorption is powerful, but it comes with a downside. The same conditions that enable fast charging also trigger super radiance, a quick and enhanced discharge of stored energy, almost like a capacitor. In earlier tests, this meant energy vanished almost as fast as it was stored. Attempts to reduce this discharge by introducing noise or disorder, called decoherence, only helped a little. To be useful, quantum batteries need a way to hold onto their charge longer.
Okay, now you mentioned capacitor. The capacitors that I'm familiar with are like in air conditioning condensers or compressors have them. Motors, they're like a charge or run charge battery. Run start.
Energy stored up for a little bit. You turn the power off and it discharges.
Yeah, or it helps start the electric device.
Yeah.
Well, once it does that, it's like the battery in your car, right? That once it starts, the alternator pretty much takes over.
Right.
Keeps the battery charged up.
Right.
And so anyway, not to get off on that. So so we're looking at slide 1, right?
Yeah.
The team at RMIT found that solution in a clever redesign. They built a battery with 2 separate layers inside a microcavity, one for charging, the other for storage. The charging layer uses super absorption to rapidly collect energy. Then the energy is transferred to a storage layer made of molecules and special properties called molecular triplet states.
And this is all shown on the slide here. Unlike regular singlet states that quickly release energy through light emission, triplet states are dark. They resist radiative decay due to rules about electron spin. Again, which means they hold on to energy far longer. These states can keep energy stored for microseconds or even minutes, depending on conditions. That's a massive improvement over the previous nanosecond scale lifetimes.
To test their concept, the researchers created 5 versions of the device. Each had slightly different energy level alignments. Their goal was to find the configuration where the lower polariton,
Yep.
Okay, energy, a mix of light and matter, matched the triplet state energy. When these 2 levels lined up perfectly, energy transfer was most efficient and storage times peaked.
In the best performing design, energy lasted for 40.3 microseconds, over 100 times longer than any previous quantum battery demonstration. This big jump confirms that decoupling energy capture from energy storage is key. It also validates the idea that dark states like triplet excitons are essential to future designs.
Quote, "Well, we've addressed a tiny ingredient of the overall piece. Our device is already much better at storing energy than its predecessor," said RMIT PhD candidate Daniel Tibbin, co-author of the study. He added that they are getting closer to creating a working quantum battery.
The batteries were built and tested at RMIT's Micro Nano Research Facility. The facility brings together research. That sounds like propaganda. Researchers from different fields to tackle complex problems in micro and nanotechnology. Their success in controlling light matter interactions and managing dark state physics highlights the strength of this collaborative approach.
There's still a long road ahead before these batteries are ready for mainstream use, but this study proves that it's possible to combine fast charging with long-lasting energy storage using quantum systems. It also hints at a future where electronics can be powered by devices that are smaller, faster, and far more efficient than today's options.
In time, this breakthrough may transform how energy is stored, especially in fields where speed and miniaturization matter. Whether it's boosting solar panel performance or powering the next gen of wearables, quantum batteries now look more real than ever before.
Okay.
I
and we've been talking about quantum stuff for a long time, right? Computing. Now we're talking about batteries. This is.
I totally didn't see this coming, quantum batteries. And when I saw the article, I was like,
obviously from your comments, you are baffled.
I am
This
baffled.
has got you baffled.
I'm trying to wrap my head around it. All right, folks. We'll see you in the afternoon. Thanks.
Take care, everyone.
He stumped the chump.